So, I would like to start by announcing that tomorrow at the exercise group, which will take place in the campus of engineering, I will join, and I would like to invite everyone to join there as well who wants to discuss about the project, in particular in deciding which direction to go, because at this early stage it's quite important to avoid that you dig very deep in some direction which doesn't make sense or such things, right? So it's actually intended to help you to get you on a track that's doable and not too difficult and not too easy either. And as a guideline, I would already say now that somehow please think, in particular if you have problems which have extremely complicated functions, to evaluate how to simplify them. That's the first thing. And then on the other hand, if you have some things that only depend on one or two variables, think if you can increase it a bit, that you have 5 or 10 or 20 variables, so that decision variables, so that it's a bit more interesting from the optimization point of view, if possible, a few more variables. So simpler functions and more variables, I guess, is a tendency that I've seen already from the descriptions last time. Yeah? Okay, just as a guiding line, and we can discuss and invent ideas. So today, and actually we have 2 more weeks left, I think, for lectures, 2 more double-hour lectures. And what we want to do, the storyline is the following. I want to conclude with interior point methods today. I have then some joker time that I would like to devote on a topic that you can decide upon. It should be either sequential convex programming. It's something that I want to share with you. Could be adjoint SQP methods, so some advanced algorithms for inequality constraint optimization. Maybe you can already think of it, because in half an hour I will ask about these topics. Yeah? And then we will start optimal control problems, which is an area where we just apply our theory to relatively large-scale examples quickly. So where you very quickly see how things get many variables without thinking too long. Yeah? Okay, we started with this section on interior point methods, and maybe I should recall what we already established last time, which is also a kind of summary. So let us recall what we did. Is we are still in the process of solving an inequality constraint optimization problem. So what we want to do is still solve a problem in a variable x that has inequalities hx bigger than 0. Yeah? That's the setting, and we remember there were some KKT conditions and we could perturb them. And what we actually decided that what we would do is we would solve a perturbed system of KKT conditions. This would be the original system of KKT conditions. This should be equal to 0, the Lagrange gradient, and then there is this KKT condition. But the KKT conditions we actually replace by something where we say mu I times hi of x minus tau should be equal to 0 for I from 1 to q. And this set of equations has exactly as many unknowns as it has variables. The variables are x and mu. And if you solve that by a root finding method, then you get an approximate solution. And if tau is getting smaller and smaller, then you recover the original solution. So you start with big tau, and then you reduce it stepwise, and each time you initialize the Newton type method with the old solution. I call it warm starting the Newton iterations, right? So these are the things that we need to take care. And one thing we also should ensure that mu I and hi of x are always positive. Because if they are getting both negative, then you could get a solution here, but that is a shadow solution that we don't like. That was the general interior point method, and we already discussed that you could define some solutions which we called x bar of tau and mu bar of tau, and that these solutions for tau going to 0, they would converge to the true solution of our optimization problem. That's what we already discussed, and intuitively this is clear, but of course an involved proof is not what we did. We will not do it. So there was one interpretation that I wanted to give to this method, which is quite intuitive and easy to derive. And so what I wanted to actually make as a remark, and that's the start of the new lecture today. We call it Remark 2. What we solve here is actually solving, it's equivalent to solving an optimization problem which has no constraints. So let's call this thing star. We could also say x bar of tau solves an equivalent barrier problem. We call it an equivalent barrier problem. And what is this barrier problem? This barrier problem will actually solve, I will just write it down, it's minimizing f minus tau times the sum of the logarithms of hi of x, where I goes from 1 to q. So this sounds like an interesting simple problem. Maybe before I go on, I would like to discuss what we do here. Is actually we have a minus and then a tau and then a log of something that should be positive. So there's something that should be positive. I could actually just take it as the x-axis, so hi. So for positive values this should be okay, but for negative values this should be a penalty. So the exact problem that we originally wanted to solve would have infinite values here and 0 values here. That was what it does, but what this minus tau, minus tau logarithm of hi, what does this function look like? The logarithm itself looks like this. So the negative logarithm looks like this. It's actually 0 at the value 1. But then if you multiply it with a tau, it will, for a very small tau, everything will, so to say, be moved towards 0, so it will actually look something like this. And you see immediately that it's, as we think, as we want, it is an approximation to this thing that goes to infinity here and goes to 0 here, which would be the perfect barrier that is just not smooth, so we don't like it. So you see that for a big tau, it would be a very smooth function. Let's say this would be a big tau, tau big, and for a tau small it looks like this, and when tau is extremely small it looks like that. So intuitively this is what we wanted, right? So it's repelling us from the boundary of the feasible set, and now let me just prove that this would be satisfying these optimality conditions. And in order to prove it we can just take the gradient of this function. Maybe I call this objective function f tilde of x and tau, maybe. And then the gradient of f tilde with respect to x, what will it be? It will be the gradient of f at x minus tau, and then it's the sum of I from 1 to q, and then I need to differentiate that thing with respect to x, but in order to do so I need to have the outer derivative of the logarithm, which will be 1 over the thing in the middle, so hi of x, and then the inner derivative, which is hi, but we take the gradient in all directions, so it's this is the gradient of this whole thing, and this is what we want to set to 0. And now let's just look what this could also be interpreted. I mean, this thing, I can just say this is nothing as writing hi gradients and each multiplied with a mu I, right? And so we see that if we would just identify minus tau 1 over hi of x, if we would identify this thing with mu I, then actually these two equations would be equivalent. But what does this mean? Actually, this is this equation. Yeah, so you see that actually the mu i's that we have here, they actually will satisfy exactly this relation. So you see that if you take, if you have a solution of this system of equations, then the x part of it will also be a solution of this system of equations. Yeah, because this equation and that equation are the same. So that's quite trivial, so we can identify these two things. And so this barrier problem is good for the intuition behind these methods. It's also sometimes used for the implementation of interior point methods. And there's generally, you can divide actually the methods into different classes of methods, and there's some methods that directly use this barrier formulation, and they don't introduce the multipliers at all, so they directly try to solve this problem. And then you speak of a primal barrier method, and or barrier or IPM method. So they solve this problem, let's say. And then there are the so-called primal dual interior point methods, and they solve this system with the multipliers or a variant of it. Yeah, so you can distinguish methods which keep the multipliers as variables. Yeah, so this is only in x, and this is in x and u.
It should be a plus before tau. Not right, it's right. Minus tau.
Right. Exactly. Wait a moment. This should be positive, so that should be with a minus sign. Okay. I think. Okay. Sorry. Yeah. Here I need a plus. This is what you meant, right? Exactly. Thank you. Because the minus sign is already there. So if I identify this with the multipliers, then I get that equation here. Okay, this primal dual methods is what usually is more efficient. I should also make one remark about the scaling of the Newton system. If you do a Newton's method on this system, yeah, with these equations, it turns out that this Newton matrices can be inverted nicely, so they are not ill-conditioned or anything. If you do this thing, what you can already imagine is that you get a very steep curvature into your problem. And it turns out that if you solve this with a Newton-type method, then there will be some extremely large entries in your Hessian matrix, which results in bad conditioning of your matrix, which can at some points lead to numerical problems. Yeah, that was everything I wanted to say here. Of course, there's lots of things to say if you want to do this in detail, but interior point methods are a class of methods that can be very successfully used for both linear programming, quadratic programming on the convex side, but also for nonlinear programming. And I will just mention this in a sentence. So IPM can be used for everything, so to say, which has inequalities. So whenever you have inequalities, you can use these methods. It can be used for LP, QP, and other other convex problems. And in this case, there is a really strong convergence theory. I should say there is something, you can have strong theoretical properties here. And they are based on a property that's called, or can be summarized on self-concordance, which I will not define. But if you want to learn about these theoretical properties, you can, so to say, look up for the word self-concordance. Basically, that holds for these convex problems when you apply the interior point method to convex problems. But on the other hand, it can also be directly used for NLP. And NLPs are, of course, the case that I have written down here already. There is some reformulations possible by introducing extra slack variables, but that's a detail. What for NLPs we don't have that strong theory. Actually, there is no global iteration bound and so on. But both in practice have strong practical properties. Yeah, both work well in practice. And that means there are competitive methods for either QP solving, LP solving, NLP solving, and so on. And what are typical codes that use these? Cplex is one of them. I mean, there are many others. Morsec is one code. There's OOQP is a code. There are many solvers for this. Actually, there are some solvers specific for other things. Forces. Dimitris, can you shout more names? Okay, I don't remember more now at the moment. Just some codes that use this. For NLP solvers, there is also several, but one of the most widely used is called IPOpt, and that's also the solver that we use in some cases. That's a nice general purpose NLP solver based on an interior point method, similar to what I described here, and it uses a primal dual interior point method. Okay, so they work well in practice, and so in some sense, one could also just say interior point methods should be the only thing I should teach you, but on the other hand, I wanted to also teach you the other methods like active set methods and SQP methods, because they are used in practice as well, and they are competitive, in particular when problems are solved again and again with slightly changing parameters. Okay. This was, not everything, because I wanted to give a very simple example, just to get the intuition. Yeah? This extremely simple example. If you want, we can make a slightly more complex example as well, but let's start with the simplest of the examples. You would just say, I minimize x, subject to x being bigger than 0, and x is element in R. Sounds very stupid, right? But anyway, that's a simple, stupid example, and that's good. So let me just write down the primal barrier for this. So what would be the primal barrier? So this f tilde would be actually x minus tau times the logarithm of x, right? That's it. How does this function look like? Here's x. For positive values of x, this is a finite function. When it's getting to 0, then this gets minus infinity, and with a minus sign, it gets plus infinity. At the value 1, you will have just this thing 0, so this is 1. So this was the original function, that was the original objective. So here the two curves cross. And for higher values, this thing will be negative. For lower values, it will be positive. So there will be something. And we could compute the slope later, but I don't know how the slope. This is, not so good, right? So what I want to do is actually something like this. Yeah. So this is the sum of the two. So this would be f tilde. This would be f. So you see that this interior point barrier is, so to say, it's somehow smoothing this corner that you would originally have. And now if you make this tau smaller and smaller, then this function gets more and more like this one. And then this tau, if the tau is small, then of course these things will still amount to nothing, while infinity will still be infinity. So very big values remain infinitely big, while all the other values will be contracted to 0, and then you get a sequence of minima that is converging to 0 here. Yeah? So you can actually define x r of tilde is actually the thing that solves this system of equations. No, this is wrong. Right? This was complete wrong. This is just setting the objective to 0, which is not making sense. I need to set the gradient to 0. So what was nabla f tilde? It would be 1 minus, and then I just wrote it down, tau. Here I would have 1 over x times the gradient of x is 1, right? So and this thing, to make that 0 means basically that the x bar tau is equal to tau, right? So we have defined the central path in this case very quickly, without Newton's method even. Once we have not one variable and maybe more complicated expressions, we cannot invert it like this, and we get a root finding procedure and so on. But that was just a simple example to give a bit of intuition. Do you want another example? Yeah, something two-dimensional. Let's just do a two-dimensional example. And let me just say minimizing something like a function. Okay, let's make it a bit more non-trivial. So I would just say I have some objective function which is a quadratic, G transpose x plus 1/2 x transpose dx. And I have only positivity constraints to make it a bit simple. But x is in Rn. So this could be another setting which is also relatively easy still to imagine. Yeah? So I want to define a bit how the objective looks here. Let me just illustrate in the 2 dimensions. I would have my quadratic objective function which has a minimum somewhere, and let's make it somehow here, for example, and there are ellipsoidal level sets. So this would be the objective function of my problem. This is the x1 and that's the x2 coordinate. So what does this barrier introduce? It makes that everything that is where this is positive is finite, and when it gets to 0 it gets infinite. So actually you get a penalty like this one in this direction, which goes to infinity here. Yeah, so it goes to infinity here, and then for the other part you get the same penalty, but it goes to infinity here. So everything which is out of this area is forbidden, of course, because it's we have our constraints, right? X should be positive, but in this penalty approach, it's actually there's an extra penalty that has level lines which are approaching infinity when we come to this L-shaped set. And because they are both actually pushing you away and they are both smooth, they will result in level lines which are shaped like this. And because they are so much dominating when it's really going up here, the level lines of the objective, here they will not be changed a lot because it's then quickly converging to 0. But at the boundary here, it converges. So what you get is actually level lines which look like this. Yeah, so these things, so to say, this whole part gets moved away because it gets infinity, and you get already the boundary here. And so somehow your minimum will now be here, pushed away by this constraint and by this constraint, and when you make the tau smaller and smaller, then the minimum will slowly approach this point, which is the solution of the constraint QP. I hope that this primal visualization helps. The primal dual thing is even more difficult to visualize, but the idea is, I think, very intuitive, and the reason why they are called interior point methods is very clear. I mean, here you are in the interior, you are not at the boundary. Here you are also in the interior, you are not at the boundary. And the interesting thing is that as long as the tau is not going to 0, you don't know actually which of the constraints will become the active ones. But then at some point you will converge basically either towards this constraint, or it could be also no constraint. So there's, they are always in the interior, and you don't know exactly what will be the active constraints. Other questions about interior point methods? Okay, so now did you make up your mind? Are you more interested in SQP with adjoints or in sequential convex programming methods today? If you don't have an opinion, I will start with sequential convex programming methods. Just to introduce a class of methods to you, which is a bit non-standard, but it's interesting and it's easy and practical to work on it. So that will be section 14.5. So sequential convex programming is in a sense a generalization of both the sequential quadratic programming and the generalized Gauss-Newton method. So I want to recall SQP and also generalized Gauss-Newton. And in particular, this generalized Gauss-Newton method, I want to recall what it did. It was a method that we used in order to solve an optimization problem where you would have an objective function which was somehow partly convex. Actually, I think we called it R of x, some residuals. That squared should be should be minimized, sorry. X was our decision variable. And then we had some constraints which had the usual form g of x equals 0 and h of x is bigger than 0. So this was the setting of the generalized Gauss-Newton method. And generalized Gauss-Newton, GGN, what did it solve in each iteration? It was solving a kind of convex approximation of this problem. And it was making it convex by linearizing this function r, this function g, and this function h. So it was exactly doing a simple thing, right? So it was saying, let's just minimize over an approximation which would actually be a Taylor series of all my functions at some iteration point xk, x minus xk, subject to g xk plus nabla g xk transpose x minus xk equals to 0, and then h of xk plus nabla h of xk transpose x minus xk should be bigger than 0. And then we somehow argued that this is a quadratic program. If you multiply these terms out, you get a special Gauss-Newton Hessian approximation, and you can solve it with a QP solver. And then you have a variant of the SQP method. But there is another point of view of looking at this whole thing. And this is actually by noting that there are two things which are convex here. One thing is actually the square function itself is a convex function. The other thing is actually that this inequality constraint set is a convex set. And in order to explain that, I just wanted to say that you could also write h of x bigger than 0. You could also equivalently write this in the form that you say h of x should be element in the positive, and we had q dimensions, in the positive numbers r plus q. So these are the non-negative real numbers. Yeah? So this is actually a set, which is the set of all the, here, if this would be one component and the other, this is a convex set. Right? It's the convex set of all positive numbers, which are where all components are positive. So actually we could write this whole thing here. So in this new language, let me just remove this picture, sorry. We could also write the original problem statement in the following form. We could also say this is actually a problem where I have minimized some function phi of r of x, and phi of y is actually 1/2 the square of y, so that's a convex function. Subject to g of x equals 0 and h of x, element in, okay, and I call this set omega. I'll just call it omega. It's maybe, yeah. Please don't confuse it now with a feasible set, which is a bit smaller. It's, yeah. This is just, I call it omega. So I could actually write this problem just in this form. Yeah? And then I could also just apply the generalized Gauss-Newton method. And what does this generalized Gauss-Newton method do? It will solve the same problem, but it will linearize the nonlinear functions. But it will not change the function phi, and it will not change the set omega. So actually I could just say, this is nothing else than phi of, okay, and now r xk plus nabla r, okay, and I will omit it because it's the same thing again and again, right? G of xk plus nabla g and so on, and h of xk, and this one I will write completely again, just for completeness, x minus xk element in omega. Yeah, here it was actually equal to 0, and here it was an element of omega. So I can actually just rewrite the whole algorithm in a slightly different form, which highlights the fact that there is a convex function phi and a convex set omega. And so the idea of sequential convex programming is just to apply the same idea to any convex set omega and any convex function phi. That's it. So apply the Gauss-Newton idea, the generalized Gauss-Newton idea to other convex objectives phi, and what I mean by other, I mean other than just squared, than sum of squares. And convex sets omega, and that means other than the positive orthant. So this is something a bit strange, but not strange, but this is what we call the positive orthant. So the positive numbers. So what could be the examples? I mean, I can make very complicated examples, or I could make less complicated examples. But what could be examples for phi? I mean, I can take any interesting convex function, right? So it need not be a squared function. It could be something like exponentials or negative logarithms. So something like exponential of x, that's convex, right? Could be negative logarithms of x, that's convex. Could be other convex functions. What do you suggest as other convex functions? Maybe something nice. Do you know this one? Log sum xi 1 to n. So this is also an interesting convex function. So all these are differentiable convex functions, and whatever you have, you could take that as your objective. And other examples for omega. What is omega? What would be these examples? You could take anything that is, for example, you just take not only inequalities, but you could also take some things like sets of ellipsoids, ellipsoidal sets. You could take some hyperbolic sets, which say all pairs of variables where the product is bigger than something. Yeah? So there are many other sets, but you could also have some things which are also including the set of positive definite matrices, for example. So you could say set of positive definite matrices. Semi-definite. So there are many possibilities. And the idea why this could be useful is because if you linearize that and you have the phi and the omega as some interesting, easy to understand convex functions, then you can actually apply a convex solver to solve this problem. And then you get your new iterate without actually having to think about linearizing these convex functions. Yeah. So these methods, SCP, relies on efficient convex solvers. Subproblem solvers. So like generalized Gauss-Newton would depend on an underlying QP solver, this might depend on an underlying SDP solver or an underlying QC-QP solver or such things. Like generalized Gauss-Newton, GGN, SCP has local linear convergence. Linear convergence in general. So it's not something with quadratic convergence speed or something. But it will converge to a local minimum, and if it's suitably damped, it can work well. So this is one class of methods I just wanted to mention very briefly, so that you have heard about them. And I just wanted to encourage you, now that you know YALMAP, if you want, you could really quickly program an SCP method with relying, for example, on this convex solver YALMAP by just relinearizing your function at the current iterate, solving a convex problem. This gives you actually the next iterate where you linearize your functions again, and then you recursively refine your guess. So that is the idea of SCP methods in a nutshell, very, very quickly. Are there questions regarding SCP? I mean, it was just an idea of this problem statement. If there's no question, I would suggest that we stop here, have a short break of 10 minutes, and then we go on with optimal control problems. I think that is what I want to do today. I would like to continue, and as promised, I want now to come to a special class of nonlinear programming problems, which we call optimal control problems. And this is in some sense just a short introduction into something that we can completely understand, but which might motivate you to think about this whole topic of optimal control a bit more, which is covered in follow-up classes, including this winter school, and also some other lecture class, which is optimal control and estimation, coming in about a year again. Okay, so this is chapter 15 about optimal control, and we look at it from our perspective that we have here. And so to just tell you, this is the aim of this lecture today is just to derive a special form of NLP. Yeah. Or derive a specially structured NLP. So So we just, at the end, there will be only an LP, but on the way to it, we will have actually to illustrate and introduce some new variable names. So our variables will not be x. Yeah. So x, what was x now, will be lots of variables together. So we will actually divide x into some classes, and we will actually even use the symbol x for other purposes now. But before I do that, I will actually introduce what the main topic of optimal control is. It's the study of how to influence dynamic systems. And a dynamic system could be something, I mean, you throw a ball and it's flying in time, right? You drive a car and you control the steering wheel. And if you think of this car, there is actually a decision you can take, and that would be the control that you take, namely if you steer to the left or to the right. Yeah? This decision you do not only take every once and then you drive to the right, but you can take it again and again. 1 second you can drive to the right, then you can drive the other second to the left. You can also do it the other way around, and then you took a different route. Yeah? So every combination of decisions is a different choice, and the study of optimal control is actually the study of how to find the optimal choices when you have a time horizon in which you can take a lot of these decisions. I think driving a car is the best example that you can have in mind. Yeah? A car will have a position, a speed, maybe some orientation, and depending on the steering angle that you apply, after 1 second you will be in another position, another orientation, and so on, and afterwards you could decide again. And so the basis is a discrete time dynamic system, and you can always imagine a car that drives for 1 second, and then you look at this state again. Discrete time dynamic system. But I will not give more examples or write it down exactly if you don't ask for it. But the dynamic system just says that there is something that we call the state, x, k, and it's determined by some map that we call f, and this map is actually depending on the previous state and on the control that we apply. So this is the state, that is the control, control, and this is the next state. And this is the system. So this map, I don't specify it, but it could be the map that applies the position of a car and the velocity of the car at one specific moment, and then 1 time step later, let's say a second later, if you keep a constant steering angle during that time, you will be in a different position and location. Another very simple example of a dynamic system, I could imagine just have this blackboard, right? So I take this blackboard to not confuse the camera, but if I apply a force to this blackboard for 1 second, then it will, okay, actually this is a very strongly damped blackboard. Maybe if I get more force, it will still have some development, right? But depending on, now I gave actually a force and then I stopped the force. I could also first apply force down, then up, and then down again, and then down again, and down again, and up. So you see this thing moves, and the state of the blackboard will be actually the position, the height, and it will be the velocity of the blackboard. And the input in this case might be the force that I apply during 1 second or the next. It could be the sampling time, could be also less than a second or more. So this is what you should have in mind when I write down this thing. It's the simulation of the system over 1 time step. Yeah, that's why we look at it in discrete time. So in practice, you could already think that there is a numerical solver behind it or something like this, a simulation routine. But we don't care. For us, we start with a discrete time dynamic system that tells you the state from at the next state depends on the old state and the control that we apply. And here, our k goes from some time point 0 to some time point n, And so this equation holds for n minus 1. So our variables of this dynamic time system are in discrete time, so they are starting at 0, and then they go here to 1, 2, and so on. And so I will have states. Here's the state x0, there is a state x1, there's a state x2, and the transitions between these variables, they will be somehow influenced by these controls and by the numbering that I chose here. An x with the same index as the q, as the u will influence the next x, and my way to visualize that is to say that this is u0, and here is u1, and maybe here is u2, and so on. So you would have u's here, and the last u will still influence also the last n, xn, but this u has the index u n minus 1. It's just a certain way of numbering. You don't need as many u's as you have x's, because there's like the last x will not, that's where everything ends, and I have no action to choose afterwards. That's the end of my time horizon of interest. So let's say I want to control this car, this blackboard, over the duration of 10 seconds, and every second I can apply another force to it. And I want to do something. For example, what I could do is that after the 10 seconds I want to be at a certain position at rest. Yeah? And maybe I want to expend as little force as possible in some measure, maybe the squared force or something that takes into account how much energy I consume when pressing. Okay, so this is the dynamic system. Yeah, we should also specify dimensions. So xk itself is element in some space, and we call the space nx. Yeah, so the dimension is nx, and uk is element in Rnu. So these would be vector spaces themselves. So please note that x is no longer the optimization variable. Yeah? It's part of it, but it's not the main one. Okay, so here we have our main object already, the dynamic system, but we could have now other things that we want, and there could be the objective, but there can be also constraints. And what we will have is also typically some things that our dynamic system state should satisfy, for example, at the beginning or at the end. So we could actually say, for example, at the beginning, my blackboard is at this position at rest. So then there are two numbers which specify the position of this blackboard. If it's at this other position and also at rest, then one number will be different, the other will still be 0. Yeah? And if it's now in this state at the beginning, yeah, then both numbers will be different. So there will be some initial conditions, but it could also be that, as I said, I want to move the blackboard to the end that it is at rest, so I could also specify some things which the last state should satisfy. And in order to express all these things in one thing, we just introduce a function which we call the boundary conditions. And this boundary condition function is something we can specify when we formulate a specific problem, but in general it is just a function of x0 and of xn, which should be equal to 0. Okay, so that is our boundary condition. And there are examples so that I make concrete what this r would be. With r is just a function from r2 times nx to, so because it depends on these two elements, to r nr. So it has possibly several components, but how many? It depends on what I specify. So I could just have a fixed initial value. So then I would just say r of x0 and xn is equal to x0 minus something that I call x0 bar, but which is fixed. So it's just a number, 5 or something like this. Yeah? Or if you have several components, it would be these numbers. That would be a fixed initial value. I could also have fixed initial and terminal value. What would it be? Then my r of x0 and xn, what would it be? It would be just a thing consisting of several components. The first nx components determine the initial value, and the last nx components determine the terminal value. And I can also have some other interesting things. I could also look for an optimal control problem where I want actually to find the optimal periodic state. So I want to move it, and I want to move it maybe between two positions, up and down. Yeah? And I want to look at only one period. And I want to require that I look at the orbit where the initial and the end state are the same, but I don't specify which value they have. I just say they should be the same. This is maybe not so interesting for this blackboard because it seems that I move between some well-determined positions, but if you think of a walking robot or a walking person, then you have a periodic motion and you want to be in the same state at the end, same apart from some symmetric motion, right? Nearly the same state after one period. The same thing applies if you have a periodic combustion engine. So inside this engine you have substances which react with each other, and you compress them, and then there's an explosion, and then there's new temperature, new concentrations. But after one cycle, your process, if you are in a steady state, in a cyclic steady state, after one cycle, the engine should be in the same state. Yeah, so you could also have periodic boundary conditions. And so how would we express periodic boundary conditions? So it's the third example. Periodic boundary conditions. How would we express it? We have just this function R. How should it be formulated? I just want that the initial and the end state are the same, but I don't want to specify specific values for them. So what thing should be equal to 0?
0.
Sorry?
X0 minus xn.
Perfect. Yeah, so x0 minus xn, or xn minus x0. Anyway, these things, that would be periodicity. Okay, so we would have different boundary conditions, and now I am already able to state the OCP, the simplest one, and I think I disagree a bit with what I did here in the script. So I will actually make it a bit more complicated at the beginning, and then we can simplify it. So this is 15.1. It's the optimal control problem formulation. So what you formulate here is an optimal control problem where you say I have an objective, so I have some things that I can decide, and I have some constraints. And what you have as an objective is very often, and that's what we use here, is actually a sum of terms which are at every time point different. I mean, there could be that a certain state, like if I accelerate, then this takes energy, and so then I want to impose a cost on it. So there's some momentous cost for it. And this cost could also depend on the state. So it's some cost that depends on x, k, and uk, but for every time step I would sum these costs up. And then it's also possible that at the end, for example, I want to throw a ball and the ball should be flying as far as possible. Then I'm really interested in what happens at the end. And so the other term that is typically present is actually the end term, which just depends on the last state. So this would be an objective function. And I write minimize now because I want more space. And let me specify a bit later what are the variables. But what should be my constraints? I want actually to choose among all possible trajectories, that means pairs of x and u, that satisfy the system dynamics and the boundary conditions and maybe some other constraints. So I want actually that xk plus 1 equals f of xk uk for the whole trajectory, and that also my boundary conditions are satisfied, xn equal to 0. And possibly I could also say that there are some things like limitations. So I could also have, for example, that the force with which I push my blackboard is limited. I mean, I cannot push it further than, let's say 5 times the gravity acceleration or something. So there will be some limits with which I can actually move this. And these limits you can generally express also in this form that you have some functions h of x. I mean, you remember some functions. I call it also h, and they should be positive, and this is for the index k up to n minus 1. Okay, and there could be a terminal constraint as well on the last state, which I could add, which I would maybe call h t for terminal of xn. That should be positive. So this would be everything that I can imagine. I mean, there might be other constraints, but these are the ones that I find the most interesting and relevant ones. And now the question, what are our degrees of freedom here? If we want these all as constraints, then our degrees of freedom are actually x0, u0, x1, u1, and so on, until xn minus 1, un minus 1, and xn. So I have a lot of variables here, some of which are actually, of course, easily constrained by this constraint. So if you look at this, you could also say, it seems that these x's are not really degrees of freedom because they are determined by that constraint. But this is not the point of view of nonlinear programming. In nonlinear programming, they are all variables, and they are constrained by this constraint. But of course, it's good and useful to keep in mind that the real thing that we can choose is probably the use. I mean, we can choose at every moment what control do we apply. And we can maybe, depending on these initial conditions, also choose the initial condition. So these are the things that we can really choose, and the rest is actually deterministically obtained by the system dynamics. But this is not something I want to focus on. I just want to look at this problem from the perspective of nonlinear programming. And just point out that this is an NLP. So, first question. So this is an NLP. And what is the dimension of this NLP? So how many decision variables? I mean, so maybe I call them W. That's, I think, how I called it here also. So I have W, and I concatenate them all. So all these things together in one vector. But W is element in what? W is element in Rn. Okay? Then we are back in the normal optimization framework that we had before. But what is N? Sorry? So 2 big N, you mean?
Yeah.
It's not exactly what I want, but it's close to it. Yeah?
2 big N plus big N plus 1.
Maybe I just collect things. So what? Big N?
Plus 1 times and x, small x, and plus big N times
Let's just count. I think that looks correct to me. So let's just remove that. But the intention is the same. Actually, this formula would be right if nx and nu would be 1, which is a bit, if you forget for a moment that these x's and u's are actually part of vectors, which I said at some point, then this would be the right thing. But if they are just not scalar, but they are vectors themselves, then it's this expression. So both in some sense are even right. But this is the one that I want. And if we count for it, it's clear we have, n times these pairs, and then the last n is at the index n, we just have one extra state. So I hope you all agree with that. So this is an NLP in some form that has an objective that depends on all these variables, and it also has constraints. And for the constraints, I just make it a bit simpler. I mean, we can always include the inequalities again. But I would like to write this as an NLP where I just have the inequalities, the equalities. So drop inequalities for a moment. And then I can just define this whole thing to be minimize big F of W. W is element in Rn. Subject to some big G of W that should be equal to 0. And then we are back in the language that we used throughout a large part of the course, right? The language of nonlinear programming. But what is the F? The function F is simple, right? So F of W is given, I mean, we have this concatenation of all these vectors, they form the W, but then this is actually the sum of the objective terms plus the terminal cost. So that would be the objective function, and clearly it is a function of W, of all the decision variables, so that is okay. Please keep in mind that our notation has a bit a mismatch with what we did before. K is now an index which just refers to a subvector of the variables. It's not an iteration index or something. It's just part of the variables. What is the G? GW would be now an interesting and complicated object that I would like you to translate, and as I said, for simplicity I want to just collect all these conditions here in one big G, which contains all these conditions. And I would also like to ask you which dimension the G has. Maybe let's first write it. Should be something that should be 0, right? So what should be 0? I mean, I can choose these things should be equal, but then I can just subtract one of them and then say this should be 0. So what do I do here? The first one of these conditions is determining, let's say I set the index k to 0, then I have, I can take it, maybe I do it the same way that I do it in the script to be, consistent, So we take the x1 minus f of x0 and u0, that would be the first condition. The second condition would be that the x2 minus f of x1 and u1 should be equal to 0. So that's the second condition. It's actually not the second condition. These are already nx conditions, and these are nx conditions because they are vector valued. But then we go on, and the last one of these is actually xn minus f of xn minus 1 and un minus 1. So this was this loop, so to say. So now we have them all together, and then there's the last one, which we already defined in some function, and that will be the function itself, x0 and xn. It will just be plugged in here. Depending on what function we had, it would be this one. If we would also have inequalities, we could also define them. I mean, it's probably straightforward. We would just go through this, concatenate all these things together, and so on. So what is the dimension of G? So G is a map from Rn to, okay, I just call it Rm. But what is M? Yeah, perfect. Thank you. So we have, again, a concatenation of lots of different quantities together. So why I wanted to go this direction is because I want to use it as an occasion to to also define the Lagrangian function and then to derive necessary optimality conditions for this. And it's an exercise in keeping track of indices and of subcomponents of vector. And so when we want to introduce the Lagrangian, I can introduce Lagrange multipliers. Yeah, so I can just introduce now the Lagrangian for this problem, and I stick to that problem here. So how would I write the Lagrangian? It would be L, which is a function of W and of lambda. Lambda being the equality multipliers, and as I said, I drop the inequalities for simplicity, and it will just be F of W minus lambda transpose G of W. So the interesting thing is that lambda will have the same dimension as G, because otherwise you cannot have a transpose. So let us define lambda to be something that we concatenate also with lots of components, and these components I want to give specific names to them. And I would like to start with lambda 1. That's the component corresponding to all these equalities. Then there's a lambda 2 here. And I go down until I'm here. And this one I call lambda n. So the index is actually determined by this thing that is determined by the equality. That's for my own convention. I like to give the lambda 1 name to this one. Please keep in mind that this lambda 1 is not just one number, but it's nx numbers. It's a vector. No? So this whole lambda is a vector consisting of all these things. And the last one we call maybe lambda r. Yeah, so for r being the label corresponding to the function r. Okay, so what will be the Lagrangian then? It will be something which consists of a sum of lots of things. And this Lagrangian can now be written down by just looking at the definitions, this definition and that one. It will be the sum from k equals 0 to n minus 1 of these terms L, xk, uk. And there will be also this, I will maybe let some space here, plus E of xn. So that's the objective contribution. But now there come also a lot of contributions which are due to these products here. And I can actually summarize all these products already. Maybe I'll do it separately. So here I have minus. I go also with the sum from k0 to n minus 1. That's just a choice, so that I go through it in the same order as I have it here. And then I multiply these things with each other, so it will be actually lambda k plus 1 transpose multiplied with x k plus 1 minus f of xk uk. This is actually the scalar product of this until here. And then I have a last term which is minus lambda r transpose times r of x0 and xn. Everything fine until here. And what I realize is that the sum is both times the same, so I could also just take the sum of these two things together, right? So the index k can run in 1. But this is not necessary to write down. I mean, it's easy to explain. The interesting thing is now we could derive the KKT conditions. So what are the KKT conditions of this? And there is actually one KKT condition which is the only non-trivial one, and that is that the gradient should be 0. I mean, the KKT conditions are nabla W, L of W and lambda. This thing should be equal to 0, and G of W should be equal to 0. So these are the KKT conditions in this big summarized form. But if we go through these KKT conditions in a detailed form, we could also write them down using the structure of our specific Lagrangian and also of the vector W. And in order to do so, I think I want to say what we need to do. So we need to somehow nabla this thing. What is it? It is actually the concatenation of a lot of gradients, namely of the gradients with respect to x0 or Lagrangian, then the gradient with respect to u0, the gradient with respect to x1, until I'm at the gradient with respect to xn of our Lagrangian. You see? So that is how the gradient will look like. The gradient with respect to some variable always has the same dimension as this variable. So these will be subcomponents, which will be gradients of the whole Lagrangian with respect to only some of their variables. And so I would like to go through these gradient components. Maybe I just start by doing it a bit here. So what will be the first one? x0. So I have here my Lagrangian. I look at this formulation here. I differentiate that function with respect to x0, and what terms will appear? Only the terms where x0 will be a part of it. So I mean, if there is no x0, so this will not depend on x0. So the derivative of this with respect to x0 is anyway not there. So there is one term here where k is equal to 0, then I have this function differentiated with respect to x. Right? So there will be actually a nabla of this L at x0 and u0. So that part will be there. Is there anything else that depends on x0 here in this Lagrangian function? Sorry? This for the index k equals 0, I think. Only there we will have it. So there will be a lambda 1, right? Minus, okay, and then here this nabla f. And as usual, actually, we will it will be easier if we just write it like this: nabla x f of x0 and u0 times lambda 1. So that is the term that we get from this. It's with a minus sign here, but there's also a minus sign here, so I actually realize that I will have a plus sign here. Okay? Is there another occurrence of x0? Yes? At the end, right? So this thing. So that will come with a minus sign, and then it is actually minus nabla with respect to x0 of this function r of x0 and xn times lambda r. Okay? So that is the first component, and we can go on. I will actually go through all these components maybe a bit separately, because this space is not enough. So let's order these things a bit, and I just go here and I just compute this thing with respect to UK. So what is the gradient of the Lagrangian with respect to UK? And k can go from 0 up to n minus 1. So for all controls I could do it. And then of course I can insert these numbers at the right places if I need to. But let's write down this UK. So where does this thing depend on UK? So we see here actually and here. And there's no other occurrence of UK. So actually we can, it looks similar like these things, but it will be with a U. So it's the derivative of L xk UK plus nabla U of f xk UK times lambda k plus 1, I think, right? Because it's always the multiplier k plus 1, which is multiplied with this derivative. And it comes with a plus sign. So this was it already. So this is the thing that is our derivative for u. x0 was a bit special, but x1 up to xn minus 1 I think will all be identical. So I should also say this thing for k going from 1 to n minus 1. I could compute these expressions here, but basing them on the thing above. And what would it be? It will be the gradient of this L with respect to xk, x, so this is xk uk, evaluated at the point xk uk. And then it will also be the term that we had already, namely this plus nabla x f of xk uk times the multiplier lambda k plus 1. But please keep in mind our convention. This is the transposed Jacobian of f. Yeah, so that was this a way of transposing things. But there was one other contribution which we didn't have for x0, but which we will have for x1 and so on. And this is something that I would like you to notice. If you go through the sum in the Lagrangian, there is another occurrence of xk, namely xk plus 1. If we differentiate that term, for example, lambda, so actually I think this sum here, this whole thing, we could also divide that sum into minus k going from 1 to n, and then here we have lambda k transpose xk, and then the other part is this thing from 0 n minus 1, and here we have now lambda with a plus sign, lambda k plus 1 transpose f of xk uk. So this is another way to write this sum. Do you agree? I mean, I just renumbered this k. Yeah, so I actually, because this k plus 1 and this k plus 1 are multiplied with each other, it runs from 0 to n minus 1, so I could also run from 1 to n and then have the index 1 lower. This way to write it reveals better where I have the xk occurring. I have it once with the k plus 1 and I have it once with the lambda k, but with the opposite sign, and it will just be the derivative of this function with respect to xk is, I mean, the gradient of that is just a unit matrix. So it will be minus lambda k times a unit matrix. Okay, so now I have written down nearly every component, but the last one is still a bit different. So this last thing, nabla xn, I still need to compute. So what is it? It is nearly the same things that appear here, but there is no part of this term. On the other hand, there is this last term due to the cost at the end and so on. So we will have nabla x of e at xn, so that will be the last cost contribution. And there will be no term of this form, but there will be this term. So there will be a minus lambda n from this sum here. That's the only occurrence of the lambda. The xn is actually the last term of this thing, and it is here. And here we get a minus nabla xn of r of x0 and xn times lambda r. Okay, so now we have collected all the equations, and we could just state what are the optimality conditions of this problem. Wait, and it gets long and nasty if you want. But the main point I would like to summarize this is actually by numbering the equations. So I would just write it again. So this nabla WL of W and lambda being equal to 0, and the G of W being equal to 0, this thing, that is equivalent to a big set of equations, which we have mostly already written down to the blackboard. So maybe I give numbers to these equations. So I give a number to this equation. This one I call 1. This I call 2. This I call 3. And this 4. And And then this is actually equal to the set of equations which comprise 1, then 2, but 2 for k from 1 to n minus 1, and then 3 for k from 1 to n minus 1, and then 4. 4 is only for 1 index. This is this part, right? This was all the equations that are in the gradient condition, but then there's the G equations. So what are the G equations? So the necessary optimality conditions also say that the G should be equal to 0, but that's trivial. I mean, that's just this thing. So it means actually that xk plus 1 minus f of xk uk is equal to 0 for k going from 0 to n minus 1. This is not surprising because it is actually the constraint of our optimization problem. It's just a restatement of the constraint. And the same thing for the boundary conditions. So they would also still be here. So here we have a big set of equations, structured set of equations. So these are depending on variables w, which are actually a concatenation of components. And themselves, these equations consist of a lot of components. And the question is how to solve them. So there are many different ways of how we can solve it. So the conclusion until now is the KKT conditions are a large structured system of equations. Nonlinear equation system. And now the question is, how do we solve it? And of course, we know how to solve nonlinear equation systems, right? We just apply Newton's method, and then we can hopefully converge to the solution. But now that the system is so structured, there are many possibilities how we could apply Newton's method. And there are two that I want to especially outline, and I think I will do one today. And the other, no, I will do both today because it's not so difficult. Variant 1. Solve this system of equations that I call maybe 5, yeah, in the variables w and lambda together, right? So now we have even more variables. All the lambdas are also variables by a Newton's method. And maybe we should keep in mind that there's sparse matrices. So you should use sparse linear algebra, because if you take this is a big nonlinear function which depends on lots of variables, namely w and lambda, but actually each component, if you look at these components of these functions, depends only on very few of these variables, so it will be a sparse system. So that's why we should use sparse linear algebra. I mean, if you differentiate that with respect to all the variables, you see immediately that it doesn't depend on anything else than the variables that you see here. And so it's actually every single equation block doesn't depend on all other variables. So this is the first variant. But the second variant is something very funny. Variant 2. You just look at these equations and you eliminate as much as you can variables. And what could we eliminate? We can eliminate the x's. I mean, all apart from x0 could be eliminated if you know u's. So you could just say, let's eliminate the x's. So that's trivial because the xk plus 1 is always appearing here as, I could just replace it by something, by overwriting it, like eliminating. Yeah? And then there's another equation where I can also easily eliminate some things, and this is this thing. Here I have the lambda k. This thing should be 0, so I could also, maybe I should call this thing here 6. Yeah? So this specific equation. And what we can use 6 and 3 to eliminate x1 up to xn. And what can we eliminate with these equations? We can eliminate lambda n minus 1 and up to 1. Lambda. No, actually, we can also use 4 because here the lambda n can also be eliminated with that equation. So we also use 4 to eliminate lambda n minus 1 up to lambda 1. And then we can see if this other equation at the top, no, that's it. We eliminate all these. And how to do it, we will maybe do it next time, or maybe I could just, no, I will not do it next time, because then I have to write all these things again on the blackboard. So let's please accept these 3 minutes overtime. Okay? That's, don't worry, if you have to leave, you have to leave, but I will do 3 minutes overtime now. Because otherwise we will not make it efficient. So now the interesting thing is that inside your variables w and lambda, there are lots of them which can be eliminated as a function of the others. So you have actually w, and it consists of x0, u0, and then x1, u1, and so on. At the end you have xn, and then you have also the lambda. How did we order these things? W and lambda together. Then you have lambda 1 up to lambda n, and you have lambda r. So these were all the unknowns that we have. And now we say we can actually eliminate lots of them. What we can eliminate is this thing. Maybe I encircle those things that we can eliminate. This thing can be eliminated. This thing, so there's an x2 and so on, up to xn. This can all be eliminated as a function of x0, u0, u1, and so on. So you can see that easily. If you specify x0 and u0, then you know x1. If you specify also u1, then you can also eliminate x2, and so on. So you see that this is easy to eliminate by this equation here. Now you can also use 3 and 4. 3 and 4. Let's start with 4. So if you would all know the xn, which you know already, and you would know all the others, and you would also know lambda r, then you can eliminate lambda n. So now I can eliminate lambda n. And I can go on recursively through these equations where I need to know the x's and the u's, which I know already from this forward elimination. But now I can, I know already lambda n, so then I know lambda n minus 1. And then I can go this loop actually backwards. So I can now eliminate all my lambdas, one after the other, until I have eliminated the last lambda. And the only variables that remain are the variables that are actually x0, u0, u1, u2, up to un minus 1, and the last thing is lambda r. So these would be the only things that I still need to have as unknowns, and from them I can eliminate everything using 6, 3, and 4. But now 3 and 4, I didn't use 2. So I didn't use this 2. So I can keep a reduced linear, nonlinear system, reduced. So I call these things maybe W bar, yeah, so that's actually a subset of the variables. And I can have a reduced nonlinear system that consists of two, the thing that I didn't use yet, but all these things I express as functions of the W bars. And there's also something else that I didn't yet use, and that is, I think, the first equation, right? The very first equation. So what you will actually get is a function g tilde of W tilde, and this function g tilde will only consist of several components that need to be zero, namely it would be the first component here. So I have this nabla x of L of x0 of u0 plus I think now I mixed too many things. So this one I shouldn't call W0. Maybe I call it tilde y, right? Because it's already comprising primal and dual variables. Just call it y tilde. Yeah? So it's more than the W. But here I have now the top component here, which is nabla x f of x0 and u0, but then multiplied with a multiplier lambda 1. But lambda 1, I should say, to be honest, because I eliminated it, is now a function of all these y tildes already. I mean, these are part of y tilde, so I can keep them, but this is also a function of y tilde after this elimination procedure. And the last thing is also this r, right? So it's nabla x0 of r. R was a function depending on x0, which is part of y tilde, so that's okay. But then I have xn. But xn, I should also make sure this is already a function of these x tilde. So I also put it as a function of this times lambda r. And lambda r is also part of my y tilde. So I see that I have this first component, and then I have all these other components, which I will not write them down. But it will be 4k going from 0 to n minus 1. So I will have a reduced system of equations that I want to set to 0, and I can also solve this with the root finding problem if I want to do it. And if you look at it, it is very funny. It is something which has only the unknowns x0, u0, u1, and so on. The things that I said would be the real unknowns, the real things that we can change. And it also contains only one multiplier, which is actually the multiplier of the boundary condition. So the interesting thing, and I will not do it because it's not necessary, but I just want to say it, is that you can actually define a reduced optimization problem where you would eliminate all the system dynamics already here in this problem statement, and you eliminate all the states before. That would eliminate all the x's as variables, but it would also eliminate all the constraints, the multipliers according to them, right? So it would be a problem which only has an objective depending on x0 and u1, u0, u1, and so on. And it would have one constraint with one multiplier lambda r. So it would have exactly the same primal dual variables as the ones that we have here. And if you formulate the optimality conditions of that reduced problem, you would actually end with this system of equations as well. The interesting thing is that the recursion here, this one, this 3, is actually something that you can interpret as a backward sweep in automatic differentiation. So what we get here, these conditions here, these derivatives with respect to u, when we insert the right multipliers here, the ones that we got from this backward recursion, then this is actually the derivative of the reduced objective function, the one where we have eliminated the system dynamics from the beginning, computed by the reverse mode of automatic differentiation, which is efficient for the Lagrangian. For the gradient of any function, it's always better to compute it with a reverse mode, and so somehow magically we derived the we would derive the exactly same Newton type method for this reduced system, either by looking at these equations and seeing what we can eliminate and then eliminating everything that we can, or by just eliminating the variables from the optimization problem at the very beginning and then applying the reverse mode of automatic differentiation to compute the quantities. Yeah? So what this is actually just saying that the gradient of this reduced objective with respect to x0 should be 0, and the gradient of the reduced objective with respect to all the controls should be equal to 0, and then, okay, this g is also not the right thing. Here I never gave a name to that, so maybe I should call this big thing not g, but how do I call it? S for big system, whatever. Yeah. So these are the primal and dual optimality conditions. Because the last one I forgot is this. No, where is the last condition? Actually, the last one is simple. It is the last one that we didn't put in is this thing, right? So this one we didn't use for elimination, but we still need it. So that's also x0 and xn, which is a function of all these variables y tilde. So that is the last thing that we also need to keep, namely the boundary conditions. And so it's basically a gradient of some of the reduced objective, or the reduced Lagrangian, and the boundary conditions. So this is a bit fuzzy, but I just, the way we derived it is clear. It was a bit tedious, but it's clear, I think. And the relation to a reduced problem is something that I would like to just throw at you, and you can think about it. So you could see what happens if I remove my x's using this equation, plug the x's into this, wherever I have an x, I plug the x in, and then I solve a problem which is already a problem in only these optimization variables. But then I need to compute the gradient with respect to these variables, and by computing the gradient with respect to these variables, and knowing that all these x's are intermediate variables, I can actually arrive at the same root finding problem. Which of the two is better, variant 1 or 2, is debatable. Yeah? So this is, if you have a good sparse solver, this is faster. If you don't have a sparse solver, this might be faster, because it's already having a lot of variables eliminated. Okay. So this was optimal control in 1 hour, a very, very rough, a quick overview, and I thank you for your attention.